to week 7 tutorial session for the course of Secure Computation Part 2. So let me share my screen and then we will discuss the week 6 assignment questions. Now that my screen is visible, so let us briefly take a overview for what was the topics covered in week 6. So the topic is mainly domain extension for perfectly secure reliable broadcast. So previously also we had seen the initial weeks of this course that how Tarpin domain extension protocol achieves the extension of a existing bit broadcast protocol to support broadcast of any L number of bits, right? But there the complexity was around order of n square L plus one single bit broadcast, but this was not optimal. So an optimal cost would be order of NL plus cost of the bit broadcast. So by bit broadcast we mean the broadcast protocol where the sender only has to send one single bit to all the parties in the system, and we expect that at the end of the reliable broadcast protocol every honest party will have the same bit as the output. So however, for supporting this broadcast protocol for any L number of bits, we now see more efficient domain extension protocols. So for that, week 6 topic starts with this warm-up protocol. So the first protocol was like this. Domain extension for RP protocol, reliable broadcast. So we try to achieve optimal communication complexity. Which is order of NL plus the cost of bit broadcast for a single bit. So of course N is the number of parties and L is the number of bits to be broadcasted, and this order of NL actually is optimal because for a sufficiently large L you like any party as a sender has anyway has to send NL bits of computation to make the bit string of length L reach to all the N parties in the system. So order of NL is the optimal cost required for any L length bit string broadcast. Now to achieve this, we start with a warm-up protocol. So there are several phases of this protocol. To start with, let's say we have a designated sender of the broadcast protocol. So this is can be any party among a set of n parties. Okay, any one party can be recognized as the sender. Now what it does is that it has a message of bit length t plus 1 multiplied with log of f bits. So this is the data that S wants to broadcast to everyone. Now why do we choose such a bit length? The reason is that we essentially want to apply Reed-Solomon decoding somewhere in the protocol, and in the Reed-Solomon decoding the message are always element of some field. So if the field has cardinality this f within the straight lines, so this is the cardinality, and so any field element then can be expressed with at most log of f, this cardinality of it. So that many bits are required to represent a field element from f, and such t plus 1 field element are there as part of or as a single message that needs to be broadcast by S. That's why this length t plus 1 into log f comes, right? So one single field element has log of f bits. T plus 1 such field element will have t plus 1 into log f bits, and this t plus 1 field element actually we can then write it as messages m1 m2 to till m, or let's say m starting from m0 to mt. Okay, so total t plus 1 elements. Now if sender treats is as the data word for Reed-Solomon encoding, then after the encoding is applied, it will turn into a code word which looks like this. So it will be C1, C2 till Cn. So here the Reed-Solomon data word length was t plus 1 field element, and here in the code word the Reed-Solomon code word length is n field element. Okay, and we can allow at most t corruption. Any t element out of this n element can get corrupted, and then still the corrupted code word can be decoded to obtain the actual message. But before going into the details of the decoding part, let's see what happens here. So as I mentioned, there are several steps to this protocol actually. So in the first stage, at first sender has these many bits. It treats these many bits as t plus 1 number of field element, and it applies RS encoding, Reed-Solomon encoding, to get this n number of field elements together as code word. So once all these things are done from the sender side, sender will simply send, so sender sends this n number of code words to all the parties. That's it. Now say if S is honest, then of course it will send the identical copies of C1 to Cn to every other parties. But if that is not the case, then also at the end of the protocol we will make sure that all the honest party reaches the same output message. Now coming back here, So this is the first step done, right? S sends the code word string to all the parties. Now in the next step, what parties would want to make sure is that sender sent identical C1 to Cn to sufficient number of parties. That needs to be ensured, right? So for that, what we do, uh, so now parties, okay, before that, let's just observe that what is the bit communication happened in this step 1. So we know that there are n number of field element and each field element can be represented using log of f bits. So there are a total of n into log f bits in here. Now these many bits are communicated individually to each of the n parties. So that makes its order of n into n log f, right? So that gives us order of n square. Log f, right? This is the communication complexity in terms of bits in the first round. And in the second round now, parties want to check if sufficient number of parties have received identical copies of C1 to Cn from S basically. And for doing that, there will be basically n C2 number of communication. Why? Let's say there are 4 parties, okay? Taking an example, there are 4 parties. Each pair of party among them will try to make sure that if they have same code word values C1 to Cn. So naively how they can check that? They can, like, P1 can broadcast its content to every other party, P2 also can broadcast all the n values to all other parties, and then they may want to check how many copies of C1 to Cn are same. So that is a huge amount of communication, as you understand. There are you see there are n number of parties, so there can be nc2 pairwise communication among all the sets of all the pairs of parties, right? So there can be if there are 4 parties, so 4c2 number of pairwise communication is possible, and in each such communication, if all the n field elements, that is n log f bits, needs to be communicated, that will lead us to n cube log f bit complexity, but that is too much, so we do not want that. So what we do, we reduce this much bit complexity by doing a clever trick that each pair of parties, say pi and pj, will exchange to each other just 2 values, right? So pi has its own copy of, let's denote it with ci1 to cin, right? And pj also has its own local copy, namely cj1 to cjn. Now pi sends to pj 2 particular component. What are they? One is PII and another is PIJ. Means the ith position field element of its own local copy and the jth position field element in its local copy. These two values are sent to Pj. Similarly, Pj also sends to Pi. Sorry, I should write it C, not P. The ith element of this array Ci, so that is Cii, and ith element and jth element of the array Ci, that is Cij. Those are sent by Pi to Pj, and on the other hand, Pj sends to Pi Cjj and Cji, right? So they know that they are communicating with each other. Pi and Pj note their corresponding IDs, and depending on that they mutually just share information of particular two positions. So there are n positions to compare with each other, but instead of comparing all the n positions of its local copy of code word, they just choose to check for equality of two particular indexes. This is really a clever tip. So as a result, what happens? After this communication is done between all such pairs of parties, so if I talk about here P1, P2, P3, P4, then there is communication between P1 and P2, P1 and P3, P1 and P4, each requiring 2 log f bit of communication from I to j and 2 log f from j to I, that is 4 log f, or in other words we can say order of log f bits of communication, right? So for each of these pairs of parties there is order of log f bit of communication. So there is P1, P2, P1, P3, P1, P4. Similarly there is P2, P3, P2, P4, and there is P3, P4. So 4C2 or 6 number of such pairs will be there, and each pair will require order of log f bits of communication, and NC2 is actually nothing but order of n square. So in total, for all order of n square such pair, order of log f bit communication is being done. So in together we can say that order of n square log f bits of communication happens in step 2, and communication is done. Okay, now what does party check? Of course, parties will check if their corresponding position values are equal. That means if Cii is equal to Cji, that is whether ith position element is same in both the copies of local keyword local code word owned by Pi and Pj, and whether jth element of local copy of code word for Pi is equal to jth element of local copy of Pj, right? So these two equality gets checked, and if both of them are true, then basically they mark a response vector, that particular position's response vector to be 1. So when I am talking about response vector, this is again an n bit length vector, it is a bit vector. So now coming to third step, after this, or maybe I am still in second phase. So in second phase there is communication happened there is computation happened, equality checking, and accordingly assignment of the response vector. So what is response vector? It is nothing but a bit vector of dimension n. So each pi will have its own response vector. So let's say party 1's response vector is r1, and r1 is nothing but a vector of dimension n, where each entry is a bit, right? Each entry is a bit, 0 or 1. And when, so r1 is the response vector of p1. Now there is some particular index, say k. Okay. Now when this vector r, kth index of vector r1 is set, it is set when the p1 and party pk are consistent with each other. So r1k, right, that means kth index of r1 is 1 if and only if pii is equal to pki and pik is equal to pkk. That means pi and pk are consistent with each other in terms of their ith and kth position value. Since p1 will, there is pairwise communication happening, right? So p1 will communicate with all the n parties in the system including itself and finds out about the consistency like this, and if it is found that positional consistency is there, then corresponding element of the response vector will be set to 1. Thus every party at the end of step 2 will have a n dimensional bit vector, namely response vector with it. Okay. Now after this phase is done, all the party will broadcast their own response vector, right? So they make the response vectors public. Now see, there are n parties and in each party has n bit of the bit vector to reliably broadcast to everyone, right? So there comes the phase requiring bit broadcast protocol for n square number of bits. Okay. So we are now after step 1. So now at step 3, each pi broadcast the n bits of corresponding response vector using bit broadcast protocol. Right. Okay. This requires whatever is the complexity of bit broadcast protocol, that is run for n square number of meetings. Why n square? Because each party has to broadcast n bits and there are total n parties, or there are total n response vector, each of length n. So total of n square number of bits needs to be broadcast in the system, and that requires instantiation of n square number of bit broadcast. Okay. Now once this response vectors for all the parties are public, we can actually construct a consistency graph. Okay. So after this n square number of bit broadcast protocol are done, everyone knows everyone else's response vector. So we now form a consistency graph. So as you know, graph will consist of n nodes corresponding to n parties of the system, and what will be the edges, right? Or what are the edges? Which of the parties will be joined together by an edge between them? That logics come clearly from the fact that if, say, party 1's response vector entry or party j, so if let's say Ri is the response vector for party I, so if Ri's entry for j is equal to Rj's entry, that is Pj's response vector entry for party I, if they are consistent with each other, then join the edge between, they are equal and they are one way, then join the edge between Pi and Pj. So consistency graph will indicate which of the parties think that both of them think that they are consistent with each other. If both the parties agree that they are consistent with each other, then only their corresponding edges are joined in the consistency graph, indicating that they are consistent with each other. Okay. Now once this consistency graph is formed, there comes the challenge of finding a click in the graph. So we have already formed the consistency graph of the parties are now computed. So next task is to find the click in the consistency graph. Why so? Because So what is a clique? Clique is a complete subset of some graph, right? If G is a graph and there is a subgraph C which is a complete graph in itself, then we say that that is a clique, right? Now if such a clique is found, actually all the honest parties in the clique will have the common code words, and if size of this clique is at least 2t plus 1, then at least t plus 1 among those parties will be honest. Then outside this clique, actually we can find other honest parties and we can make them have the same code word as of the parties inside the clique by simply applying a majority value over all the communicated response vectors from all the parties in the clique, right? So so in this manner, actually all the honest parties agree upon common code word, okay, by taking majority value communicated from the core of cardinality at least 2t plus 1. Okay. So then everyone actually will again do a communication of its local so basically what happens, all the honest parties outside so if there is a party pi, so if pi is outside core, so core is consisting of the clique only, so we call the clique with cardinality at least 2t plus 1 to be the core. So if pi is outside core and it is honest, what it does is this: if it is not honest, we cannot determine its behavior, so we are just focusing on honest party. So an honest party outside core, it assigns value cii, so it initially had a local copy of all the n elements of the code word, right? ci1 to cin. Among them only ci it will correct, so it will correct ci as the following: cii equal to majority of all the, so majority of the set of cji, so these values, all the cji values where pj belongs to core, we can write this. So for all the parties in the code, whatever is the value of ith index of its local copy, if pi from outside the code takes the majority of those values, it will actually have cii to be same as ith element of all honest parties in code. It will be same as the ith element of all honest party in code, and all the honest party in code already have same data, same code word with them. Okay. So in this manner, actually pi can assign correct value to its ith element. So at the end of this step, right, at the end of this step, each pi has a correct value of cii, so it sends cii to all other parties. Now let's say there is p1, p2, p3 and p4. So p1 will send the value of c11 to everyone, right? Similarly, p2 will send the value of c22 to everyone. Okay. In the view of p1, p1 receives c11 from p1, it receives c22 from p2, receives c33 from p3, and it receives c44 from p4. Now p1 will modify its local copy of code word as c11, c22, c33, c44, right? And same will be done, by p2, p3, p4 also. So every one of p1, p2, p3, p4, all of them will have the local copy of code word modified as c11, c22, c33, c44. Now not all the parties are honest, of course. At most t parties can be corrupt, maliciously corrupt. So among these, let's say if we consider 1 out of 4. Now among these 4 parties, value sent by the parties to each other, at most one of them could be a wrong value. If p3 is a corrupt party, it may choose to send different values of c33 to different parties. So this value of c33 will not be a reliable value, but at most t such value can be incorrect out of n values in the modified local copy of the code word. So each party individually now performs a Reed-Solomon decoding. So perform each pi, each honest pi to be more specific, performs RS decoding on this C11, C22, C33, C44, right, to get back what M0 to MT, right? Why is this possible? Because the length of code word minus the length of data word is indeed greater equal to 2t, that t is the irregularity capability of the irregularity code, which means n is actually greater than 3t, and that's why the RS decoding works correctly, and we get a reliable broadcast protocol for t plus 1 into log f number of bits. Now one can modify this warm-up protocol to support so this protocol is further improved to support any arbitrary L number of bit broadcast. I should not write bit broadcast for L number of bits, where L is some multiple of t plus 1 log f. So t plus 1 log f now becomes the unit length to be broadcast using the warm-up protocol, but then b such blocks are there of equal size such that L is b into t plus 1 log f. The b number of blocks are there, so b number of instances of warm-up extension protocol is required. However, we have seen further optimization in a intermediate round so that it keeps the bit complexity at order of n square log f plus this many bits complexity will be required. However, finding a key is not a easy problem, or there is polynomial time algorithm for doing that. So we then shift our attention to NT star graphs, right? And we have shown that if there is a graph having click of size at least 2t plus 1, then there will be a empty star graph satisfying the conditions for empty star. So in an empty star graph there is essentially two subgraphs, say C and D, such that C has a cardinality of at least n minus 2t, whereas D will have cardinality of at least n minus t. D is a superset of C, and the most important constant is that all the nodes in C must be having an edge to all the nodes in D. Okay. For example, So let's say this is a click, right? And then we add say 3 more nodes such that each node of C is connected to each node in D. Like this. So there are 3 nodes, there are 4 nodes in the clique, right? So let's say A, B, C and D, and there is E, F and G. So all of A, B, C, D, they are in a clique, right? And each of A, B, C, D has connecting edge to all the nodes in D. So okay, there is a problem in the naming, but so let's denote it with calligraphic C and calligraphic D. Here is this. So you see that although the nodes in E, F, G are not connected with each other, there is no edge between E and F, there is no edge between F and G, or there is no edge between G and E, but all the nodes in C are connected to all the nodes in D. So we have so basically NP structure satisfies things like this, and with such NP star graphs found in our finding core part, we can properly use some expansion mechanism to get a core with number of parties at least 2t plus 1, so that the honest majority thing can work in the modified setting as well, right? Anyway, so now with this small overview of the week 6 topics, we proceed to discussing week 6 assignments. First question is match the phase in the warm-up protocol to the communication complexity used for that phase. So there are options: code word distribution, announcement of response vector, pairwise consistency check, and obtaining code word from code. So all these problems we discussed just now. So code word distribution is the very first step where the sender sends all the values C1 to Cn to each of the n parties in the system. So C1 to Cn are nothing but n number of field elements, and each field element can have bit length at most log of cardinality of f. So n log f amount of communication is required for sending a message from the sender to any one of the party, and since there are total n number of parties, we will require n square log f number of bits. Okay, so 1 matches with A. Next option is announcement of response vector. Now this one also we saw that there are n number of parties, and in each party has a bit vector of length n. So a total of n square bits needs to be communicated or needs to be broadcast. So for that purpose we use the reliable broadcast protocol for a single bit, and this is getting used for n square number of times for n square bits. So 2 maps to B in the right side column. Then there is pairwise consistency check. Here also we saw that there are NC2 number of pairs possible in a system of n parties, and each such pair actually checks whether their corresponding bit positions are consistent with each other or not. So two field elements are sent from Pi to Pj, and two field elements are sent from Pj to Pi, and there are NC2 number of such communication, and that's why in total there is a requirement of order of n square log f bits of communication. So pairwise consistency check, point 3 maps to point A of the right column. Last option is obtaining code word from code. Again I just mentioned that each Pi sends the value Cii to everyone else in the final phase of our protocol, right? So basically each party broadcasts one field element to all the n parties. So n log f amount of communication is done by one party, and there are n parties, so order of n square log f amount of bit communication is required. So we get 1 mapping to A, 2 mapping to B, 3 mapping to A, and 4 mapping to A. So this is the correct answer. Next question. Suppose that we try to perform domain expansion using an NT star CD for 40 less than n. Choose the correct option from the following. So previously we saw that for the correctness of Reed-Solomon decoding, and in the domain extended version of perfectly secure reliable broadcast, we were considering a scenario where the corruption threshold T is less than n by 3 or n greater than 3T. But here we are trying to consider a scenario where n is greater than 4T. Now what happens? The option says parties in C can form a core set of parties which have the same code word such that more than T honest parties belong to code. Now let's recall that when we talk about empty star graph, right? So the CD satisfy this condition, right? So C has a cardinality greater equal to n minus 2T, and D will have a cardinality greater equal to n minus 2. Since n is greater than 4T, we can write this as greater than 2T. So previously what happened, to get to declare the C as the core for a NT star graph, we had n greater than 3T, so we had C to be greater than T, or in other words C to be greater equal to T plus 1. Since among them at most T parties can be corrupt, so at least one party would be honest, right? in this case, previous case. But in this scenario, since c is greater than 2t or it is greater equal to 2t plus 1, and among them at most t can be corrupt, this means that at least t plus 1 is honest in C. And so parties in C actually can form a core set of parties which will have same code word, and more than t honest parties can be there in core. The next option says parties in D can form a core set such that more than t honest parties belong to core. Now with the same logic, here we get, since n is greater than 4t, D is actually greater equal to 3t plus 1. So clearly there are among 3t plus 1 parties at most t can be corrupt, so at least 2t plus 1 honest party will be there in D. So parties in D can form a core. Not only that, notice that for getting a core set, we require this condition, right, that core size has to be greater equal to 2t plus 1. So this is satisfied by both C and D in this condition. So the first option and the second option both holds true. The third option says there is no need to expand the star to find sets E and F for 40 less than n. Clearly we went for expanding CD to E and F respectively because our C and D did not have the sufficient cardinality to be declared as a core set, right? Only if core set has a cardinality of 2t plus 1, we then can argue that there must be honest majority among the parties in the core set, and we can exploit that to assign the index wise correct element for each party pi. So each party pi assigns correct value to its element Cii only if there is honest majority in the set core. But if it is not, then we cannot apply that property. That's why for n greater than 3t condition, any CD in the empty star graph did not have the sufficient cardinality to be considered as core. It did not have necessarily the cardinality more than 2t plus 1. So we went for expanding C and D to some set E and F so that the core set can have cardinality at least 2t plus 1. However, in case of n greater than 40, we already can see that the cardinality of C and D are at least 2t plus 1. So they themselves can form a core set. So we don't anymore need to expand them to E and F. So it is true that there is no need to. Last option says one cannot find an empty star when S is honest for n greater than 40. Well, this is not true, because if S is honest, then if S is honest, S must have communicated identical copies of C1 to Cn to all the parties in the system, and all the honest parties in the system, after receiving the identical copies of C1 to Cn from honest S, they will be essentially consistent with each other. So there must be a clique consisting of all the honest parties, and if there is a clique of sufficient length, there must be an empty star graph existent there. So last statement is not true. If S is honest, then of course one can find an empty stub. Next question says, Professor X said that the block size chosen when dividing the message of size L bits is very important in the domain extension protocol based on RS error correcting codes. Which of the following options is or are correct regarding the block size? First option says a constant block size will help improve communication complexity since the size of the polynomial used to encode the code word will be smaller. Second option says a constant block size won't help to achieve the order of NL communication complexity. Third option says a block size greater than t plus 1 log f cannot be used since error correction may not be possible. And the fourth option says a block size greater than t plus 1 log f will further help improve communication complexity and at the same time achieve all security properties of domain extension. So they are talking about the particular bit length L. So we were discussing the warm-up protocol where we considered only this much of length bit string to be communicated, but to generalize this, we considered in the next protocol we considered any L bit length string such that L can be written as a multiple of this t plus 1 into log f, right? Now what if we just choose some constant block size? So instead of choosing it as t plus 1 log f, the reason being, so why did we choose t plus 1 log f to be the block size at the first place? That is because we can consider it as t plus 1 number of field elements. But if we don't want to do that, we want to go with a fixed block size, then actually it will not help us gain the order of NL communication complexity. It will not even like make the protocol running currently. So as we said that there was the role of Reed-Solomon encoding and Reed-Solomon decoding. So we cannot choose any arbitrary length block size. We must map them into a valid message encoding polynomial and perform the encoding. Also, if this is constant, if you remember that when we upgraded from a warm-up protocol to a protocol supporting any arbitrary L bit length, we concluded that running B instance of the protocol, the warm-up protocol, will give us a protocol for any arbitrary length bits. So there this formula came to play that B into order of n square log f. So this part, since B is nothing but L by block size, which is log of f in our case, so replacing B with L by block size into the complexity n square log f, and t is order of n, so one n could be cancelled and log f is cancelled, so we could write this as order of n. But if we replace this block size with some constant, say k, and then there is n square log f, we don't get rid of this n square term, there is some constant present, so it will be like order of n square n. But to get order of NL complexity out of this, we need a block size like this. That's why a constant block size won't help to achieve the order of NL complexity. A block size greater than t plus 1 log f cannot be used since error correction may not be possible. That is quite trivial to see, because t plus 1 log f means t plus 1 number of field elements in the message encoding polynomial. If we take a greater block size, that will make the number of data word greater than t plus 1, right? Now we know that in RS decoding, read Solomon decoding, we need this condition that number of field element in the code word minus number of field element in the data word, so let's denote it with m, should be greater equal to 2t, right? Or in other words, m should be less equal to n minus 2t. But if m is more than t plus 1, right, let's say t plus 2, this is not true, because n minus 2t is already what I am saying is this, that if let's say we take some value more than t plus 1 here, okay, so previously we had data word size t plus 1 in place of t plus 1 into log f bits, but if we take more than that value, this is actually greater than 2t plus 2. No, this is greater than 2t minus 2, right? So n minus t plus 2, n is the size of code word, t plus 2 is the size of data word if we are using block size greater than this, so this will be at least t plus 2, and n minus t plus 2 is greater equal to 2t minus 2, because n is greater than 3t, right? So, but this value 2t minus 2 is not greater than 2t, right? But we require that code word size minus data word size remain greater equal to 2t in order to ensure correct RS decoding. So this is a true statement that a block size greater than t plus 1 log f cannot be used, since error correction may not be possible. And consequently the last option becomes false, because it says that block size greater than t plus 1 log f will further help improve communication complexity and at the same time achieve all security properties of domain extension. Since statement 3 is correct, statement 4 is of course false. Okay. Coming to next question. Suppose that n is the set of matched nodes, t is the set of triangle heads, and m is the matching found in G prime. G prime is nothing but the complement graph, right? So the set of nodes in G prime is same as set of nodes in G, but set of edges in G are not there in G prime, but the edges which are not existing in G, right? So if two nodes are not connected to each other in G, then it must be connected to each other in G prime. So the edge set is complement to each other, right, in G and G prime. Now question is, which of the following statements regarding the expansion of star C comma D to C comma E comma F to find core is or are correct? There are few options. Suppose that S is honest. So if S is honest, what happens basically is that S will send all the copies of C1 to C1 identically. So all identical copies of C1 to Cn will be transmitted to the parties, and all the honest party will receive the identical copies of C1 to Cn. So in the consistency graph G, all the honest parties must be connected to each other because they will be consistent with each other. Now the question says that if this is honest, let Cn be the product parties which are matched with an honest parties. Okay, before that, what is matching? So matching is in a graph matching is a set of nodes, set of edges, right, such that they do not share any common vertex, right? So each of the edge, so all these edges does not have any pairwise common vertex, right? So this is kind of matching. Okay. Now Cn is the set of product parties which are matched with an honest parties. So let's say there is some node A belonging to Cn, that means it is matched with the honest party. So B. So this is a honest party and this is a product party. And Ct is set of product parties which are adjacent to an honest party which belong to T. T is the set of triangle heads. So if you remember from the lecture, what is triangle head? Triangle head is a node. So a node belongs to triangle head if it has or it is adjacent to two nodes which are two ends of a matching edge, right? So I mean that if there is an edge in the matching between some party I and party J, so this is a matching edge, and there is a party T who is adjacent to both I and J, then this is a element of triangle head. Now Ct is a product party. So any element of Ct is product, but it is adjacent to a honest party which belong to T. So if there is a honest party T which is a triangle head, so it must be of this form. So this is element of Ct and this A node is element of Cn. Now question is about the intersection of these two sets, Cn and Ct. So first option says that Cn intersection Ct is phi. Second option says that it's not equal to phi. So phi denotes null set, right? So if there is any element common between Cn and Ct, that we need to figure out. Also note that in NT-star finding algorithm, we always deal with the complement graph G prime instead of the original graph. So if we need to find out that whether it is possible that there is some common element between Cn and Ct. So let's say we first assume that there is an element x. So there is an element x that belongs to Cn and Cn intersection Ct. If such X exists, what will it look like? So this X is an element of Cn. So X is a product party that has a matching with the honest party. So this is a matching edge in the graph. X is also an element of Ct. So elements of Ct are adjacent to honest party that belong to T. So if X also belongs to T, it must be adjacent to a honest party, say H2, let's denote it H1. This is honest party, this is another honest party, which is a triangle head. So if this honest party is a triangle head, then it must satisfy this kind of structure, right? So this is a honest party which is a triangle head, and this product party X is adjacent to this. Now let's understand whether this is possible in a graph if S is honest. So one thing to notice is that we are in G prime, right? In G prime there is a matching edge between X and H1. X is product party, H1 is honest party, and in G prime there is a edge. So X is adjacent to another honest party H2, where H2 is a element of triangle head. So H2 has adjacency with both X and H1. That means there exists an edge between H1 and H2 in G prime, which implies in G, H1 and H2 are not connected. There is no edge in G. So an edge between H1 and H2, two honest parties in G prime, implies there is no edge between two honest party H1 and H2 in G. But remember that S is honest, so all the honest party must be consistent with each other, and there will be an edge in the consistency graph. So it cannot be possible that there is no edge between two honest party in G. So our initial assumption was wrong by contradiction. So there cannot be such an X, node X in the, or party X in the system of n parties, which is element of both Cn and Ct. So our first option is actually correct option, that intersection of Cn and Ct is a null set. Clearly this option is wrong. Third option says that since T plus 1 parties will belong to C when S is honest, the domain extension protocol will work even without extending the star. Okay, so this may not be said with certainty, right? Because when S is honest, then there will be a star. Of course, there will be existence of a empty star graph, but whether there is a need for extending, that cannot be guaranteed, because n is greater than 3t, and in that scenario the length of C is more than equal to t plus 1, right, or at least t plus 1, among which at most t can be product. So only one honest party will be there in C. So there is a need of extending C, otherwise our core formation cannot be done, because in core formation we need at least 2t plus 1 elements in the core such that honest majority is there. Proceeding to the next question. Given the below graph, select the correct option for the set C and D found using the star finding algorithm with t equal to 2, assuming the matching found in the complement graph is m equal to 3, 4, 2, 5. So we run the match find algorithm in the complement graph. So if I draw the complement graph here, so in complement graph there will be edge between 2 and 3, edge between 2 and 5, and there will be edge between 1 and 5. There will be edge between 3 and 4. So 3 to 2, 3 to 4, 5 to 2, 5 to 1, 4 to 3, 1 to 5. So this will be the complement graph. If this is G, then this is G prime. Now in the complement graph the matching is 3, 4. So this is and 2, 5. This is, of course they do not share any common vertex, that is okay, and there is no edge between so there is no common vertex, that's okay. Now how do we then proceed with our star finding algorithm once the matching is found? So once the matching is found, we basically proceed to finding the, so there is C and D. So our C will essentially be the vertex set minus set of unmatched minus the set of matched nodes, right, which is n, and the set of triangle hits. Now matched nodes are here, of course 3, 4, 2, 5. So v minus n becomes 1, and we will again subtract the set of triangle hits from here. Now is 1 itself is a triangle head? Let's check. So to be a triangle head, 1 must have to be adjacent to 2 such nodes who are having a matching edge, but that is not the case here. 1 is adjacent to only 5. If 1 would be adjacent to 2 as well, then 1 could be a triangle head, but here that is not the case, so 1 is not a triangle head. So C is just 1. Okay. Now by looking at the option, you can already see that only option containing C equal to 1 is this, so this must be the correct option, but just for completeness let's check the D set also. So D set you find in this manner. If you remember, the vertex set minus B, where B is the set of parties, set of matched nodes who has a neighbor in the C set, right? So the matched nodes are 3, 4, 2, 5. Let's say among them who has an adjacency with the nodes in C. So C contains only one node, which is 1, and 1 is adjacent to 5 only. So among 3, 4, 2 and 5, only 5 has adjacency to the node in C. So 5 is in B. So if we just remove the elements of set B, which is only 5, we are left with D equal to 1, 2, 3 and 4, right? So that is how we get C and D here, and here you can check that by definition each node of C should have an edge with each node of D. So you can see D is 1, 2, 3, 4, so 1 has indeed edge with 2, 3 and 4, but with 5 it does not have an edge. So 5 is not included in D, but D is 1, 2, 3. Okay, so this is all about the week 6 assignments. Now we briefly discuss the week 7 topics. So in week 7 we basically see perfectly secure verifiable secret sharing protocol. Why is that needed? Because so we in this week 7 we actually want to see a BGW protocol for Byzantine corruption setting. So we want to achieve that. Now how BGW protocol works? Basically works on arithmetic circuits represented by addition and multiplication gates, and gate invariant is an important factor here. Gate invariant what do we mean by that? So let us say there is two party A and B computing the same thing. So let's say they both want to compute x1 plus x2. A has private input x1, B has private input x1. So what A does? A shares x1 into multiple share. It keeps with it x1 one share of x1, and it keeps with B another share. So A basically sends the value x12 to B, but B, by seeing x12, B cannot determine x1 in its whole because it is completely unaware of another share x11, right? So this is just a very naive example to show that what do we mean by gate invariant. Now on the other hand, like the way A gives x12 to B, B also shares x2 into 2 share, keeps x22 with itself and gives x21 to A, right? A also, after seeing x21, cannot determine anything about the x2 in whole. So A is still oblivious of x2 and B is still oblivious of x1, but both of them can perform actually this. So A has x11 with its own, and A also receives x21 from B. So they add them up, and B also have x12 with it and receives B has x22 with it and receives x12 from A, and it adds them up. So x11 plus x21 and x12 plus x22, these two, if you notice, is actually additive secret share of x1 plus x2, right? Because if you add them together, you will get nothing but x11 plus x12, you get x1, and x21 plus x2, you get x2. So you can add the individual shares to get the final result x1 plus x2. So although there is this application of addition gate, the way individual inputs are shared among parties, even after the application of the gate, the outputs are also shared in the same manner among the parties. So here I assume just simple additive secret sharing, that is x1 is x11 plus x12 and x2 is x21 plus x22. But for a t out of a threshold setting, we can make use of threshold secret sharing by Shamir, where there can be multiple parties A1, A2, A3. So let's consider it 2 out of 5 setting, right? So x1 will make Shamir secret share of its own input x1, A2 will also make Shamir secret share of its own input x2, and so on. Now, before the starting of application of some gate, all the inputs will be Tn secret share, Tn Shamir secret share. But after the application of gate also, by the linearity of Shamir secret sharing scheme, the outputs will also remain Tn secret shared among the parties. That is the beauty of the linearity of Shamir secret sharing protocol and the gate invariant of the BGW. However, all this works in a semi-honest setting, or where the adversary just looks at the transcript or the communication between the parties, but does not tamper them or does not modify the contents. So it did not participate actively. But now in active corruption setting or malicious or Byzantine corruption setting, a corrupted party can potentially send wrong values. So let's say after application of some gate, A1 has a share Y1, A2 has Y2, A3 has Y3, A4 has Y4 and A5 has Y5, such that Y is 2,5 secret share among the parties. And Y is some intermediate get out. Okay. Now when the parties are willing to reconstruct Y from Y1 to Y5, they need at least T number of shares from T parties, right? Now let's say A3 is a corrupt party, and when A1, A2, A3 come together to reconstruct Y, A1 correctly supplies Y1, A2 correctly supplies Y2, but A3 can choose to supply some different value, so that the whole computation of Y or reconstruction of Y gets wrong. So Y will not be reconstructed. So this is not expected, right? In the Byzantine corruption scenario, we would expect that the system remains robust even in presence of such Byzantine adversaries. And there comes the question of verifiable secret sharing. So we can clearly see that summit secret sharing in its standard form is not verifiable. What do we expect from verifiable secret sharing? Essentially two properties. One is that if the dealer is corrupt, right, if the dealer is corrupt, then the dealer should be caught, because dealer means who is doing the initial secret sharing and distributing among the parties. The dealer could be one of the parties also. So if in this 2 out of 5 scenario A3 is the dealer who is corrupt, then at the very beginning while sharing the its own input x3, instead of giving the real shares of x3, it can distribute all the fake shares of x3. So instead of x3 1, it gives x3 1 dash to a1, it gives x3 2 dash to a2, and so on. So every party will receive some random values which has nothing to do with the actual value of x3. Then the whole computation will go wrong. So the first target of VSS, or verifiable secret sharing, is to first detect corrupt dealer in the sharing phase. So any secret sharing protocol essentially has two phases. One is sharing phase, where the dealer just shares the secret among multiple parties, and then another is reconstruction phase, right, where some t plus 1 number of parties come together to reconstruct the value of the secret. Now in the sharing phase, verifiable secret sharing should ensure that the dealer is not corrupt, right, and even if it is corrupt, it should follow some protocol such that it may not share the actual shares of some x3, but it has to be consistent with some secret x3 dash, right. It should not be some random values, right. Even if a3 is corrupt, the verifiable secret sharing must ensure that x3 1 dash, x3 2 dash, and so on should be valid shares of some x3 dash. If not of x3, it should be valid shares for some other secret, right. So that is to be ensured by a verifiable secret sharing protocol. And then there is another target, which is to detect corrupt parties during reconstruction, right. So during reconstruction, if some party is contributing a wrong share instead of the actual share, then that should be caught. So these are the target for verifiable secret sharing. In this week we have not yet seen some instantiation of real verifiable secret sharing protocol, but we have seen that a study of bivariate polynomials over finite fields that has been initiated. So we have already seen several properties of univariate polynomial. For example, if there is a polynomial of degree t, then any t plus 1 points on that polynomial uniquely determines the coefficient of the polynomial, or it gives unique polynomial. Also, if there are two degree polynomials, then they will intersect at most t points. So all these properties we have discussed and exploited in the protocols that were designed previously. Now they actually move forward to bivariate polynomial. So instead of a single variable, now the polynomial will consist of two variables in the form of x comma y, and there will be terms like x some coefficient into x to the power 0, y to the power 0, then say c01 x to the power 0, y to the power 1, say c10 where it is x to the power 1, y to the power 0, and there is say c11 where it is x to the power 1, y to the power 1, and so on. So these kinds of term, that is, you can see, so in univariate polynomial you used to see only like some constant, then like this, right, and so on. But now you will find terms like xy, x square y, xy square, x square y square, only x, only y, something like this, so on. So all these terms will be present in. So usually previously we dealt with t degree univariate polynomial, and now we will be dealing with t comma t degree bivariate polynomial, which means that both x and y can have degree at most t in the expression of the polynomial. And then we have seen discussion among several properties of bivariate polynomials, and how a bivariate polynomial can be reduced or can be collapsed to a univariate polynomial when we replace the value of either of the variable x and y with some constant value. So if we replace the value of x in the expression of bivariate polynomial, we will get a univariate polynomial in y, and similarly if we replace the value of y with some constant term in a bivariate polynomial, we will get a univariate polynomial in x, and so on. And then we have also seen that how any t square plus 1 point, so you can easily see that just like univariate polynomial, where for a t degree polynomial there are a total of t plus 1 coefficient in the array, right? For example, if we say 2 degree polynomial, 2 degree univariate polynomial over some field f, right, then it has the form c0 plus c1x plus c2x square. So there are a total of 3 coefficients, right, and each of them can take any value from the field. So there are a possibility of total this many such univariate polynomials, right? Similarly, if we now talk about 2, 2 degree bivariate polynomial, what it would look like? So it will have c0 plus c10 x c20 x square and c11 xy c12 xy square c x square y c01 So the other so a total of t plus 1 square points are there, that is 2 plus 1 square. So this many points are there, so you will get this many possibilities of 2 degree bivariate polynomial, right? Okay, now if you fix the constant term of such bivariate polynomial, then we denote the set. So let's say C0 is fixed to S, then all the TT bivariate polynomials with a fixed constant term S, this set has a cardinality of t plus 1 square minus 1, because one element is fixed, rest of the elements has still possibility of taking value, any value from the set. Okay, so there are several properties discussed, right, about the bivariate polynomial. We will further see some more properties in the next week also, and then we proceed to getting some meaningful verifiable sequential. So this is it for this week. Thank you.